We're going to look at a couple more examples with counting with combinations. Combinations are ubiquitous. They help us count a lot of different things. And on the outset, when we're dealing with combinations, we like to use this notation n choose r. Equivalently, combination of n comma r. And you may even see it listed like this in certain calculators. I encourage you to do a quick Google search on your specific device and counting these, because we don't really ever use the formulas, specifically because this is n factorial over n minus r factorial times r factorial. A lot of times when n is really big, the calculator simply will overflow. You'll get an overflow error. So there are buttons in the calculator to do this computation. It's not important that you do it by hand with the formula. And we also know that the permutations of n things taken r at a time is almost the same thing, but we don't eliminate the duplicates. So the difference here is that this one, for example, counts both AB and BA. And so basically this would count these as two distinct items. So if it's important that A comma B is going to be different than B comma A, then we do need to count those two as being separate and different. So let's say person A the first person gets the managerial position and the second person is a customer service representative, then A comma B is different than B comma A. Similarly over here, if we did have AB and BA, then because we're dividing out the number of arrangements of those two items, which in this case would be 2 factorial, 2 times 1, there's 2 possibilities for the first element, 1 possibility for the second, this divides that out. So we're not going to count this one as being different than A comma B, and so we're only going to get 1 possibility here. Now if you have 3 possibilities, so think about this formula as n factorial over n minus r factorial. That's going to give you the same answer that this would give. It's exactly the same formula, but we're dividing out, we're removing essentially the number of ways the same r objects can be rearranged within themselves. So in this context, if we have, for example, A, B, C, A, C, B, BAC, BCA, and then we'll also have CAB and CBA. And if those are all being treated as the same thing, if these are just 3 positions being filled, and the 3 positions are equal, there's no difference between them, then we may not want to count all 6 of these. We may just want to treat this whole block of 6 arrangements as one. Well, if you think about how these are arranged, there are 3 possibilities for that first one, 2 possibilities for that second one, 1 possibility for the third one, which is really just 3 factorial, and that's the number of slots we're trying to fill. So dividing by this r factorial will basically treat every 6 groupings as being the same, and therefore we'll divide out those replicates. Again, there's a button for this in the calculator, there's a button for this in the calculator as well. In our first problem here, we want to know how many bit strings of length n contain exactly r ones. Well, let's take a look at an example. If we have n equals 2 and r equals 1, this means that we are only filling, we're looking at a bit string of length 2, and we want exactly 1 1 in there. Well, there's 2 possibilities. That 1 could be here, or that 1 could be there. Now, in terms of what we can have in this slot, this could be a 0 or it could be a 1. And if the second digit is the 1, oh, I'm sorry, no, because we have exactly r1s, that's the key word here. So that means that the only possibility here and here would be for this to be a 0, this to be a 0. So there are really just 2 ways that can happen. Now, if we had n equals 2 and r equals 2, well, that means that we're going to have exactly 2 1s, and there's only 1 way for that to happen, right? 1 1 is no different than 1 1. They're both 1s. They're both the same element. So this is just going to have 1 possibility. Well, if you notice, what this ends up being is that this is 2 or the combination of trying to fill 2 slots with just 1 1, with exactly 1 1 to be exact. And if we calculate this, we're going to get 2, which is exactly the number of ways that we were able to make that happen. Over here, notice that if we took 2 things, 2 at a time, in other words, I have 2 slots, I want to fill them with 2 1s, that's going to give me an answer of 1, telling me there's only 1 way for that to happen. Now we can keep building this up and we can keep kind of exploding this. We could say, let's say that you have n spaces. You have n spaces. So this is position 1, position 2, position 3, all the way up here to position n. So to get exactly r ones in there, let's say 2 of them, well, the 2 could be here, the 1 could be here and here, or the 1 could be here and in slot 3, or it could be in any one of these all the way up to this nth one. So that would be the number of ways that we could have a 1 in the first slot with a 1 in some other slot, zeros everywhere else. So that's going to give me, well, let's see. That's going to give me, by itself, it's going to give me n minus 1 possible ways I could have a 1 in the first slot and a 1 in any other slot, zeros everywhere else. But that's not going to become very helpful because now we need to consider if that 1 right here is shifted to this position, then we need to consider all of those possibilities. But a more pragmatic way of thinking about this is I have n items and I want to fill r of them. So instead of writing this as choosing r objects, we're basically choosing r of these slots into which to put a 1. So that means that in general, if I have n slots and I want to select r of them, well, what am I doing when I'm selecting r of them? By selecting r of them, what we're really saying is fill any r of them with 1s. So that's going to be a combination of n things taken r at a time. So if r is 100 and n is 250, we would have combination 250, whatever I said, 50 of them. So this tells us how many ways I could fill r slots out of a total of n of them with exactly a 1. In this next example, here we have 9 faculty members who are in the math department and 11 who are in the computer science department. How many ways are there to select a committee to develop a discrete mathematics course at a school if the committee is to consist of 3 faculty members from the math department and 4 from the computer science department? So we really have 2 things going on here. One, we need to select 3 committee members from the group of 9. So we have to ask ourselves immediately, how are we going to use permutations or combinations? Well, does the order in which the 3 faculty members are selected from the 9, does that matter? In this case, it doesn't because we're simply forming a committee. So no role is different than any other role. So A, B, C and B, A, C are really going to be treated as the same thing in this context because it's the same 3 people acting on that committee. So immediately that tells me that there are, in this case, 9, choose 3 of them to form the committee of 3. Now, from the 11, I want to select 4 faculty members, and again, they're the same roles, so from the 11, I'm going to select 4. Now, what do I do with these 2 things? Well, the answer is we're going to multiply them together. But to provide a little bit of intuition, let's say that here one of the possible arrangements of selecting 3 from the 9 is ABC. And remember, that's the same thing as BAC, BCA. So by using a combination, we've already excluded those 5 other ways of arranging ABC. Now, here I'm going to select 4 members, and just for the sake of fun here, let's call these. We'll call this. Maybe we'll use F, G, H, and I. Okay, well, one way to form the committee is for us to have the 3 faculty members from the math division, A, B, and C, and connect them with those specific 4 faculty members from the computer science department. Now, another possibility here is we want to pair A, B, C with, for instance, G, H, I, and J. So 3 of those committee members are the same, but notice that now J is in there, so these 2 are different because they consist of different people, at least by one individual. So because if I were to draw this tree diagram, I would have all these different pairings of A, B, C with all the different pairings of the 4 selected from the computer science division. That tells me that I want to multiply these 2 together. So we have combination 9, 3 possible groupings of 3 people from the 1 division, and each of those groupings needs to be paired with each of the groupings from the 11 choose 4. My answer is going to be, and I could, again, calculate this in my calculator, or I could use some sort of web applet to compute combinations, but the product of these 2 will tell me the total number of ways I could basically form a committee of 7 members, 3 from the 1st division, 4 from the 2nd. Well, what if we recrafted this and we said, just as sort of a follow-up to this, what if we just needed 7 total members? Well, in this case, we don't really care, or the way this is worded, we don't really care where those 7 come from. They could all be math faculty members, or they could all be computer science majors. So, computer science faculty. So in this case, what we really have is we have 20 people from which to choose. And again, the order in which they're chosen doesn't matter because A, B, C, D, E, F is going to be the same thing as A, C, B, D, E, F. So in this context, we would have 20 members from which we're going to select 7. And that's when we would bundle them together. Keep in mind that doing it this way is going to count the possible ways in which all 7 of them could be math faculty members, and there's more than one way that could happen because there's 9 faculty members, and it's also going to include all the ways in which 7 faculty members could be chosen strictly from the computer science department. It's also going to count things such as 6 math faculty and 1 computer science faculty, and that would be the advantage of bundling them all together if we were not concerned about the construction of this committee.